In our so far in the network and information security class, we have discussed the security fundamentals, then also cryptography fundamentals, then we have seen classical cryptography, then we have seen symmetric encryption techniques, so in this we have seen DES, then we have seen AES, right? Of course, when it comes to DES, we have seen DES, double DES, meet in middle attack, and triple DES. Then we have discussed the advanced encryption standard. Okay, so these are all about symmetric encryption techniques. Now the point is, when discussing about symmetric encryption techniques, while introducing the cryptography, we have narrated the with regard to the key, how do actually we differentiate the various so if you notice the symmetric and asymmetric crypto systems, the difference, we are submitting the same key for encryption, so probably you can think it as from the sender side, and this is happening the decryption at the receiver side. So we are submitting the same key for encryption and decryption purpose. So the challenge involved with the, of course, we have discussed DES encryption, we have discussed AES encryption, which is coming under the category of symmetric crypto system. Okay, so the onus of the major responsibility or the major onus is how to securely transmit or exchange the key. This is the major challenge in the symmetric crypto systems. Okay, so both at sender and receiver, how do they have the common key? I can make a robust encryption algorithm, and I am going to use a larger key size. But if I do not share my key in a secured manner, the whole exercise is lost, right? So as I keep giving this particular example, you are vacating your hostels and you kept all your items in a big iron box, and you have locked it. Now the box goes via a courier guy to your native place. Now in order to open that particular box, you need that key which you have used to lock it. Okay, the same key has to be used to unlock that particular box. Certainly you cannot send that same key with the same courier guy along with your box. So that has to be sent in a different channel. So probably either you can carry the key while going from hostel to your native place, or maybe you can send that key via a different courier channel, so that once the box is delivered at your home, the key also comes from a different courier fellow. So back at home, someone can open the box with that particular key. So that is the typical scenario of symmetric crypto system. So the challenge is how we are going to securely transmit the key. Now, imagine if we don't have the need to securely transmit the key, in the sense I encrypt with one particular key called KE, and if I decrypt with another key called KT, so your KE is not equal to KD. Okay. In such case, do I have the burden of securely transmitting the encryption key in this scenario? In the second scenario, do I have that burden of securely communicating the encryption key in the second scenario?
No, sir.
I don't require, because I am using one key for encryption purpose and I am using a different key for a decryption purpose. So I need not worry about this securely transmitting the key. So this type of scheme is called asymmetric crypto system, where my encryption key is KE and my decryption key is KD, and KE is not equal to KD. Okay. Such type of crypto systems are called asymmetric crypto systems. Now, with the help of asymmetric crypto system, what is the major challenge we are able to overcome? The major challenge is we need not securely transmit the key. So key exchange need not happen at all. So you need not worry about the key exchange. So you focus only on the encryption and decryption. That's all. Whereas in the case of symmetric crypto system, you have the burden of looking after not only the encryption and decryption process, but also the burden of exchanging the key. So that burden is not there in the asymmetric crypto systems. So if you look at the asymmetric crypto systems, generally the common what I say, the notion is that people think that asymmetric crypto systems are more secure than symmetric crypto system. No, it is not that. So there is nothing that the asymmetric crypto system is secure more than symmetric crypto system. So first of all, such type of notions don't have such type of notions. The point is only one advantage, or the advantage that the asymmetric crypto systems is having than symmetric, is that you do not have the burden of exchanging the key. That's the only advantage that you are able to achieve. Okay, so you cannot compare that symmetric is less secure, asymmetric is more secure, or vice versa. Say symmetric is secure and asymmetric is more secure. No. Okay, so please do not come to such type of conclusions. Are you able to follow what we are discussing?
Yes, sir.
Yeah.
Yes, sir.
And then, so once the public crypto system or the asymmetric crypto systems that are introduced, we have a lot of advantages, in the sense, number one, you have overcome the problem of exchanging the key, number one. Number two is that you need not worry about typical substitution and permutation operations. Now, if you notice, our AES and the DES algorithms are typically based on these two operations over the plain text, right? In order to achieve, what is the goal of substitution? What is the goal of substitution? Is to confuse. Permutation goal is to diffuse. So the asymmetric crypto systems, they don't depend upon such type of activities. Okay, essentially they are based on purely mathematical functions. Then, okay, so asymmetric crypto systems is purely on mathematical functions than your substitution and permutation operations, right? So why you call asymmetric? The reason is that you have one key for encryption purpose and you have another key for decryption purpose, and hence you are calling it as asymmetric. Okay, so two different keys. And in addition to that, in addition to this particular advantage of a key distribution or key exchange problem, you have a lot more advantages with asymmetric crypto system. Number one is that we are able to achieve authentication. Number one. Number two, we are also able to achieve the digital signatures. Okay. So these are all the byproducts of the asymmetric crypto system, right? Now, how actually these asymmetric crypto system typically work is that, now imagine you have Bob and you have Alice. Okay. Bob and Alice. In the previous case of symmetric, both are using the common key. Now, in the case of asymmetric, Bob will have a pair called KE1, then KD1. Okay, a pair of keys. Similarly, Alice also will have her pair KE2 and KD2. Okay, so it's a pair. Now, Bob has a pair, Alice is having a pair. One key for encryption, another key for decryption. Similarly, one key for encryption, another key for decryption. KD stands for decryption key, KE stands for encryption key. Okay, and Bob key pair is KE1, KD1. Alice pair is KE2 and KD2. Now, among these two keys, one key is kept public. Okay, typically the encryption key is kept public and the decryption key is kept private. Similarly, on the Alice side, encryption key is kept public, decryption key is kept private. That means when I say private, it is not known only to Alice and it is not known to anyone else. When I say public, it is known to everyone. Okay, in addition to Bob, even Alice also, and Bob, anybody in the network knows this particular key. Are you able to follow?
Yes, sir.
So now the point is, since we are performing the encryption process with the help of a key called KE, which is kept public, the asymmetric encryption is also known as public key encryption. Okay, or asymmetric key encryption. The reason for calling it as public key encryption is that you are using the key which is kept public, that key you are using for encryption purpose, and hence it is called as public key encryption. Similarly, when we encrypt with one key called KE, we are able to decrypt it with another key called KD, hence it is called asymmetric key encryption. Okay, I hope you are able to follow. Now the point is, imagine Bob wants to send a message to Alice in a secret manner. How Bob would send the message to Alice? Bob takes a message M that would be encrypted with the help of Alice public key, that is KE2. So I am going to write here for the clarity purpose. E of M comma KE2. What is KE2? What is KE2?
Public key.
Public key of
Alice.
Public key of Alice. So Bob is going to use public key of Alice to encrypt the message and send that particular message, which is the ciphertext, to Alice. Now Alice receives this particular message and decrypts it and get back the plain text as M is equal to D of, that means the decryption over the ciphertext with the help of her secret key, that is KD2. Okay, KD2. What is KD2?
Private key of Alice that only she has.
So Alice has private key of her. Of course, she has the pair. She has a public key. She has a private key. Bob has used Alice public key and encrypted the message. Alice is using her private key and decrypting the message. Now, Alice is using her private key and hence only she will be able to decrypt that message. Can anyone else be able to decrypt the message? Certainly not. The reason is, if at all to decrypt it, in order to perform the decryption, anybody who wants to perform decryption, they need the private key of Alice. The reason is it is encrypted with public key of Alice, and hence if you have to perform decryption, for that we need private key of Alice. Now who will have private key of Alice? Only Alice will have, because it is private to her, and hence the message is confidential. Are you able to follow?
Yes, sir.
Any doubts? Now imagine Alice is sending a message to Bob. Alice is sending a message to Bob. When Alice is sending a message to Bob, she will take the message, encrypt it with the help of, say M1 is the message, she will encrypt it with the help of public key of Alice, that is KE1. Public key of Bob. Okay, public key of Bob. So Alice is sending a message to Bob. She is going to encrypt that message with the help of public key of Bob. So once Bob receives the message, Bob would decrypt it with his private key. Okay, so get back the plain text M is equal to D of C comma KD1. Okay, since the decryption key, which is a private key of Bob, only Bob can decrypt the message. Right? Is that process are able to follow?
Yes, sir.
Any doubts?
No, sir.
So I said Bob is having a pair KE1 and KD1. Alice is having her pair KE2 and KD2. Now in order to message from Bob to Alice, how it goes? C is equal to E of M comma which key?
KE2.
KE2. Okay. And after once the Alice receives it, Alice will get back the message M is equal to D of C comma KD2. So encryption happened with whose key?
Alice's public key.
Alice
KE2.
public key. Who is Alice here? The receiver. So receiver's public key and decryption with receivers private key. Is it not?
Yes, sir.
Similarly, imagine if Alice is sending a message to Bob. In such case, C is equal to, say I'm just writing C1. C1 is equal to E of M1 is the message. Then which key?
One.
Which key? KE1. So at the receiver, that means now Bob is the receiver. Bob decrypts it D of C1, and what is the key? KD1.
One.
So we are using encryption with the receiver's public key, decryption with the receiver's private key. Means you have to understand the logic here that when I take a pair like KE2, KD2 or KE1, KD1, when I am using KE1 for encryption purpose, I am supposed to use KD1 for the decryption purpose. Okay. So my pair, I am supposed to generate the pair for Bob, similarly for Alice, and whomsoever that is there in the network. I have to generate the pairs like this, KE1, KD1, KE2, KD2, such type of pairs I have to generate so that encryption is possible with the key of the pair, and decryption is also possible with the key in that same pair. Okay. Now, the point is it that I should use always receiver's public key? What will happen if I am going to use the sender's keys? Now imagine Bob is sending a message to Alice. Now the message is M, C is equal to E of message, comma, I am encrypting with private key of Bob. I am encrypting with private key of Bob.
Sir, the public key is with everyone, so they're actually encrypting the message.
Sorry?
Sir, the KE1 is public key and everyone has it, not just Alice.
Correct.
So the
Exactly.
encryption is not
yeah,
useful.
that is true. That is true. That is true. So now the point is how I am going to decrypt at Alice. The decryption is through D of C comma KE1, which is public key of Bob. So encryption with sender's private key and decryption with sender's which key?
Public.
Okay. So now the point is, as someone rightly mentioned, I am using for encryption purpose the private key of Bob. Bob has used his private key. No one else can use that private key because only Bob can encrypt that message. Because Bob only knows his private key. Now, at the decryption is supposed to be done with the help of public key of Bob because it is encrypted with the private key of Bob. So the decryption happens with the public key of Bob. So Alice will be able to decrypt the message by using the public key of Bob. But the question is it that Bob public key is known only to Alice? Of course, certainly not. When KE1 is the public key would be will be known not only to Alice but for everybody in the network. So this type of performing encryption would not provide confidentiality. So there is no confidentiality. Anyone can decrypt the message. Whereas the scheme that is shown above provides confidentiality. Okay, because the encryption is happened with the receiver's public key and decryption is happening with the receiver's private key, and only receiver knows that key. and hence the message is confidential. No one can decrypt it. Whereas here you are encrypting with the private key of the sender and the decryption is happening with the public key of sender. So there is no question of confidentiality here. But it serves one particular purpose. The purpose is, if you notice the first scheme, you are able to provide confidentiality. That means Alice receives the message, and certainly when the encryption is through public key encryption, Alice would decrypt the message with the help of her private key and gets the message. But now, would Alice know who actually sent the message in authentic manner? Anyone can encrypt the message because Alice public key is known to anybody, not only Bob, even Eve can do the encryption, Darth can do the encryption, anyone can do the encryption, and Alice can do the decryption. But Alice would certainly not know who is the sender of the message. So there is no authentication here, source authentication. Whereas if you notice the second scenario, there is no confidentiality because the message can be decrypted by anybody by using the public key of the receiver. Okay, sorry, public key of the sender. But this particular scheme provides authentication in the sense, once the Alice receives the message, in order to perform the decryption, what Alice has to use? What Alice has to use in order to perform decryption in the second scenario?
Use Bob's public key. So in a way it will.
So the Alice should use Bob's public key. That means Alice is able to understand who actually has sent this message. So the source authentication is possible with the help of encrypting with using sender's private key. Message confidentiality is possible by performing encryption with receiver's public key and decryptions with receiver's private key. Are you able to follow the both schemes? So case 1, no authentication and confidentiality. Case 2, no confidentiality but authentication. Are you able to follow? Any doubts?
No.
Hello?
No doubt.
Now, the point is it that I can achieve both? Can I achieve both? Both, that means confidentiality and source authentication. Can I achieve both? Of course, we can achieve both by combining both these schemes, case 1 and case 2. Right? Before I proceed to that, let us all understand, first of all, if you notice these schemes, both case 1 and case 2, they're all based upon the pair of keys, encryption key and decryption key for every node. So number 1, when we are going for the asymmetric key encryption techniques or public key encryption techniques, there are certain requirements. What are the requirements? Number 1, you just don't focus only on the encryption and decryption process, but also on the key pair generation. This is more important, the key pair generation. My KE1, KD1, similarly KE2, KD2. I need to generate such pair. So that is a very challenging task here in public key schemes. Why it is challenge? It is challenge. The reason is, first of all, if you notice, number one, I am generating two keys, KE1, KD1. And remember, one key is kept public, that is KE1, and one key is kept secret, KD1, right? Remember, I am using a pair. In the pair, I am keeping one thing is public, one thing is private. And I am using one key for encryption purpose, and I'm using another key for decryption purpose. Now we know that the decryption is exactly the reverse process of encryption. So when I am performing the decryption, if my encryption key and decryption key, if they are totally not related at all, will my scheme would work? Certainly it would not work. So there should be some kind of a relation. Now, when I'm having the relation, the question is, among the two, one is kept public, but another one is kept secret. If attacker, by knowing something public, which is KE1, will he be able to calculate KD1? Then what will happen? What will happen if attacker, knowing the public key, if he is able to calculate the private key? What will happen? What will happen here? Nothing will happen.
Yeah, he'll be able to get the message.
Not only that particular message, right? See, there are two things. If you lose the message, the loss is only for that particular message. If you lose the key, what will happen?
All future communication is breached
That's
forever.
all. That's all. See, you have you have with you, say, 1 lakh rupees, right? So you have kept 1 lakh rupees in a safe, and you are having 100 rupees in your pocket, in your purse. If you lose your purse, you are losing with only that 100 rupees. Imagine if you lose your safe lock, not only this 100 rupees, your that 1 lakh rupees has gone. The similar manner, the point is that if you lose the key, is such a catastrophe. So the point is, the KE1 and KD1, they are supposed to have some kind of a relation, so that having encryption with one key, you are able to decrypt with another key. There should be some kind of a relation. But having relation should not lead to either calculation or reducing of the secret key by having a public key. Is it not? Do you find such a requirement or not here?
Yes, sir.
So that's the major requirement. So how do I generate such key where I'm going to keep the relation, but certainly that relation will not reveal the clues to the attacker, so that by having the public key, he is able to calculate the private key. So that is the major challenge in the public key crypto systems. Now we have certain challenge in the symmetric crypto system, where how to share the secret key. We said, okay, that is the headache. Why not we introduce a scheme where I'm going to have one key for encryption, another key for decryption. So I'm able to solve that particular challenge of secretly sharing the secret symmetric key. Now the point is, by coming to this particular scheme, we have another overhead. Of course, that problem is solved, but this has introduced another requirement. Okay, so now, so this is the requirement. Essentially, the requirement for the public key crypto system is that your key pair generation, in the sense that, first of all, I must be able to generate the key pair. When I say I must be able to generate the key pair, wait here, you will be able to generate the key pair next 5 years time. No, it's not that way. I should have computationally feasible algorithm that generates the key pair depending on my type of application, right? So a computationally feasible algorithm that generates the key pair. Now, that is for the key generation. Now, once I have the key generation, I should have a computationally feasible algorithms for using that one particular key performing encryption process and using the different key and perform my decryption process. So these are all the various requirements of public key crypto systems. So please go to your book and understand, read and understand requirements of public key crypto systems. Right? Now, after understanding or realizing there is an importance of, there are certain requirements of the public key crypto systems, and after seeing the two cases where we are performing encryption with the help of receiver's public key and decryption with the help of receiver's private key, and another scheme where encryption has happened with the sender's private key and the decryption has happened with the sender's public key, and both they are achieving as one confidentiality, the other one source authentication. Now, how do I combine both? Yes, I can combine both and achieve both through like this. Now, if you notice, uh, if you notice, the scheme here is we are going to use for encryption algorithm. One minute. Give me a moment. This is not the diagram. So if you notice, this is the source. So this is, you can think it as Bob, and this is Alice. So now what Bob has done, he took the message and submitted to the encryption algorithm with the help of the private key of the source. That means private keys of Bob. So private key of sender. Okay, you can think it as KD1 or PRA. Okay, so private key of A, which is the source. Okay, so you get a ciphertext. Okay, which is called intermediate ciphertext. Now that particular intermediate ciphertext is again encrypted with the help of public key of sender. Are you able to follow? Are you able to follow? So we are performing encryption two times, at the source or at the sender. So first encryption happened with the private key of sender. So encryption with the private key of sender achieves what? If you perform encryption with the help of private key of sender, gives you what?
Authority.
Sorry?
Authorization. We can know who the source is.
So you are able to get source of the message. That means authentication of the source. Right? When you perform encryption with the public key of sender, sorry, public key of receiver. I'm sorry, public key of receiver. If you perform encryption with the public key of receiver, what is that you achieve?
Confidentiality.
You achieve confidentiality, right? So when the source Bob sending a message to Alice, initially Bob has encrypted the message with the private key of Bob, took the intermediate ciphertext, again encrypted with the public key of receiver, that is Alice public key. Now this is the cipher, actual ciphertext. Okay. Now that actual ciphertext is sent to the receiver, the destination. At the destination, Alice has to perform decryption twice. So this first decryption is reverse of the last encryption. Okay, so this particular decryption is reverse for this particular encryption. So if for that purpose, this particular encryption is happened with the public key of Alice, and hence this decryption is happening with private key of Alice or receiver. So you get the intermediate ciphertext. For that, again perform decryption, which is the reverse process of this particular encryption. So for that purpose, so this encryption happened with the private key of the sender. So this decryption is happening with public key of sender. That is Bob. Okay. So this gives you both confidentiality as well as authentication. So this is the scheme what we discussed. Initially, private key of the sender is used for encryption. Again, public key of the receiver, so that you get the actual ciphertext that is sent. And at the receiver, first you perform the decryption of the last encryption. Okay, and then perform decryption of the first encryption. Okay. Is that clear? So we are able to achieve both confidentiality and authentication. Right? Hello?
Yes, sir. Yes, sir.
Are you able to follow?
Yes,
Yes,
sir.
sir.
So these are all the various fundamental concepts of public key crypto systems. If you notice, you have multiple applications. Okay, so depending on the application, the sender is able to use or the sender's private key or receiver public key or both. Okay, so what is that you can achieve? Number one, you can achieve typical confidentiality, encryption and decryption. You can also achieve the digital signature. Okay, that means the authentication. Okay, and above that, you can also achieve key exchange. When I say key exchange, typically key exchange is will come at where? When you are using symmetric encryption, right? What is the challenge in the symmetric encryption? What is the challenge in symmetric encryption?
Sharing the keys.
So how do I share the common key between Alice and Bob? So what I can do here is I can use asymmetric crypto system for exchange of symmetric keys. So for exchange of symmetric keys. Okay. So you have a challenge with the symmetric crypto systems. I can solve that problem of securely exchanging the common key through asymmetric crypto systems. Now, there are several asymmetric crypto systems. Most popular is the RSA algorithm. You have Diffie-Hellman key exchange algorithm. You have elliptic curve cryptography algorithm. You have digital signature schemes. Okay, so there are various algorithms that we will be discussing in the upcoming classes. So as I've said, there are various requirements of public key schemes. Um, so yeah, so these are the various requirements of public key schemes. So please go back and read it so that tomorrow class we will start the RSA algorithm. So essentially, number one, every party, every node should be able to generate the key pair. Okay. So when I say PUB, PRP, that means it is your PE, KE1 and KD1. Okay. Similarly, it is computationally easy for any node knowing the public key of the other node. That means the receiver's node, the sender node is able to generate the ciphertext. Okay, that means encryption is possible with the help of one of the key. Similarly, decryption is possible with the help of, when I say possible, remember computationally easy. Okay. Decryption is possible at the receiver side with the help of the other key in the pair. That means the private key. Similarly, it is computationally infeasible for an attacker having known the public key and able to calculate or recover or the calculate, deduce, or whatever it is, either the other key, that means the having known the public key, able to calculate the private key. That should not be possible. Computationally, it should be infeasible. Similarly, the plain text. Okay. And I must be having the flexibility to apply the encryption with the help of in any order, like we have seen the scenario, right? Achieving both confidentiality and authentication, the order of the key is important. Okay, so I can apply in any order. Okay, so that should be possible. Okay, so these are all the requirements of public key crypto systems. So in the next class, we will start RSA algorithm, which is the widely deployed public key encryption standard. Okay. Any doubts?